the static equilibrium title. We addressed our names and PeopleSoft IDs for you guys, and we went ahead and initialized our housekeeping commands, which is clear all, close all, and CLC. We needed the close all because of our plot. We went ahead and incorporated our problem statement and have everything nice and neat. We said that we should write a script that incorporates the concepts of static equilibrium to determine the tension forces and angle theta. In addition, evaluate the maximum length that one of the cables can be to maintain the corresponding relationship to the tension. So in commented out green, we have our inputs. D is equal to the distance between A and C in feet. Then we have W is equal to the weight of the block, and LAB is the length of the cable from point A to point B. So the very first thing that we did was we went ahead and brought in our Excel file here. So data equals XLS read P3 statics. Brought that in, and we went ahead and did a data validation. A simple thing, moving cell by cell, row by row, column by column. We initialized 2 for loops and made sure that each value was greater than 0, and judging by, as shown by this conditional here, if the data RC at whatever row, whatever column was less than 0, then the new data value, the data of RC, should be the absolute value of that data value. And we tested this multiple times and it worked efficiently and correctly. So so we were proud of that. Then we went ahead down here and extracted each variable. Lowercase d is equal to the first column in feet, the first column of our P3 statics. Lowercase w is equal to the second column in pounds, and LAB was equal to the third column in meters. We did 2 conversions here, 2 major conversions, and we converted from capital D is equal to lowercase d times 3.28084, and that's simply just going from feet to meters. And then we also have capital W is going from pounds to newtons. So that way we could have SI units of statics and physics, so that they would work a little bit better with our equations. Another data validation step that we did here was to make sure that LAB was always less than D. So I initialized a counter here and said for X is going to, starting at 1, going to the length of LAB, so every value of LAB. And if for some reason that LAB was greater than D of X, then the new LAB value we said, we gave kind of a warning message to the user and said LAB value is greater than the distance D between the points A and B. Please enter a new value. And the reason why we did this was so that we could make sure that 1, to do the data validation, and 2, to make sure that the user could input and replace that value. We saw a couple extra credit opportunities. You'll see them in green throughout my code. Unfortunately, we did not happen to get to them, but I would like to share with you guys and make sure that you guys understand that some of these opportunities would have been slightly interesting to see implemented. One of extra credit opportunities that we saw was maybe entering or having the specific value that is being replaced, like maybe having the location or the actual value in this specific for loop data validation step. Another extra credit opportunity we saw was to validate that LAC must be less than the combination of D and LAB, which is the simple triangle theorem, which I will explain in depth a little bit later. And we also saw an opportunity to do the unique function, where just in case in our Excel file we had multiple values, it would take the unique of them and make sure that we didn't have any repeating values and everything was working efficiently. We went ahead and went into our calculations and had 2 for loops as our base. The first one is going from 1 to the amount of rows, and we initialized our max LAC here. The reason why we can do this before we initialized LAC, the array, is because that the max LAC is dependent on D and LAB. So simply stating that the maximum LAC would be assuming that LAC was the hypotenuse of the triangle. So we simply use Pythagorean theorem here to find our max LAC, stating that it was the square root of D squared plus LAB squared. Next we went to our array that we defined, and the bare minimum value that it could possibly be was LAB of y. Because in that case, if it was, then you'd have an isosceles triangle, where two of those sides are the same, and we thought that that would be the bare minimum that it could possibly be. And then we're increasing by increments of 0.1 and going to the max LAC value that we just defined above this line here. Then we go into our second for loop, and we say that we're starting at 1 and going to the length of LACs, whatever that array's length has to be. So we're doing every single value in the array. And we went ahead and here, this commented out green section, we were trying to implement that triangle theorem, as I was saying, stating that any two sides of the triangle added up together must always be greater than the third side. So we were trying to implement that, as I was saying. However, we weren't able to do so in time. All of our outputs in our function here are because we needed to create an array, we used n, because we wanted to make sure that they are running for every single value of LAC, whereas every single of our inputs here we used y, which is the counter defined in the outer loop, because we want to make sure that they stop after each row of our original Excel file. We don't want these to be n's because we don't want it to run for every single value of the array, because there would be more values in the array than there would be in our Excel file, hypothetically. Moving on, this is our function file here. We used the law of cosines to find theta. We solved for theta and simply stated that theta is equal to the arc cosine of d squared plus LAB squared minus LAC squared divided by 2 times d times LAB. So the reason why we did that was the law of cosines is quite an obvious thing to use here, and beneath that, to find phi for our tension equations, we just used the law of sine. Underneath we have our tension equations TAC and TAB. The first one we were finding TAC, and we used theta, and what we did was we said that the absolute value of W times cosine of theta divided by sine of theta plus pi would be equal to our tension AC force. And for our tension AB force, we said that the absolute value of W times cosine of phi is equal to sine of phi plus theta to find our tension of AB. We wanted to get to our plotting, however, unfortunately we were having some odd issues with that. Unfortunately, I wasn't able to make this run without messing up our code. So I know we'll probably get points off for that, but that's okay. And yeah, that is our project. Thank you very much.